in session 5.2, I'm going to introduce you a time harmonic plane wave. And in the last session, I promised you that we're going to start this introduction on electromagnetic wave slowly. In this session, we'll also be doing some review so that you can catch the concept easily. So you're going to see that you could have seen this in the past in my previous lectures. And I want to tell you a plane wave solution from the wave equation. And we want to deal with time harmonic field. So we write this time harmonic field into phasor notation and factor out this exponential j omega t. And so in the last topic of the session, I told you that if you just keep this in the wave equation, you can get this Helmholtz equation. And don't forget that this k is called wave number. That is equal to 2 pi over wavelength. And we want to get a solution from this Helmholtz equation for this electric field. And at this moment, we just guess there's a solution like this. And when I talk about guessing solution, it does not mean that this guessing solution gives you all the solutions. It could be just one of the solutions. And this solution is particularly interesting. You're going to see later on that this solution, in fact, tells you a plane wave. So let's start with this guessing solution, which is an amplitude, a vector amplitude, multiplying with exponential j minus j kxx minus j kyy minus j kzz. And we can write this into a short notation. Just define k as a vector having 3 components along x, y, z directions. And this r, in general, is a position vector. So with this definition, you can write this electric field into this short form. You have the amplitude in front of it, and then multiplying with the exponential minus j k dot r, where k and r are vectors. And so you substitute this guessing solution into Helmholtz equation and try to find out the limitation or constraint on this the kx, ky, and kz. And it turns out that once you do this Laplacian on this guessing solution plus k squared and this e in this Helmholtz equation, you come up with the constraint on this ks, ky, kz. Specifically, is k squared equal to ks squared plus ky squared plus kz squared. And remember that once you have the solution in phasor form, then you can convert it into a real solution by doing this practice. You put the phasor here and multiply it with exponential j omega t and take real part of it to recover the final real solution. So let's do it. Assume that you get a solution correctly, and then you multiply it with exponential j omega t. Then you come up with the real solution. And again, if you adopt the short form of k dot r, then this solution is quite compact. So you have a vector amplitude in front of this cosine, and the argument inside this cosine is omega t minus k dot r plus phi 0. And phi 0 is the initial phase. And in the past, we saw this before, and we also know that the complex part of this expression is the complex amplitude of the field. Now, we want to figure out what this form will tell us physically. And so I want to remind you that in the past, we know that a wave must have a wavefront. And a wavefront is a constant phase plane. So that's just pick up the phase of your solution and then set it into a constant. And then try to figure out how this equation will define a plane in space. And again, let's adopt the short form. So this the kx x plus ky y plus kzz equal to constant can be written into this k vector dot with r vector. And we can extract the magnitude of this k to be this symbol k, and then this an is the unit vector of this k. And then we start to see what the geometric meaning of this expression. If you still remember when we talk about the vector dot product, geometrically it means that we are doing the projection of k onto, say, r direction, and then multiply these two together. So it tells you that the projection of this r onto this k, or projection of this k onto this r, is a constant. So let's look at this diagram. Suppose that in space I have r position vector telling you a position in space, and then I have a vector k in space going along this an direction, and this an dot r equals a constant. Is equivalent to say that you project this r onto this an direction, and you always get a constant length if this r is a position in space. So apparently with this construction, you understand that all the r position will fall on a plane. Because on a plane, if you just pick a point on this plane and project it along the certain fixed direction and require it to be a constant length, this means that this point is going to be on a plane. And now you understand that why this k vector is called the wavefront vector, because this plane defines a wavefront for the wave. And sometimes we just call it the wave vector. And also that it's now understood that this expression, the solution, is a plane wave solution, because the wavefront of this wave is a plane in space. And now I want to summarize a little bit for this session. In this session, we argue that this is the solution for plane wave, even though it's the guessing solution. And again, a guessing solution is not a complete solution. It's just one of several solutions to the Helmholtz equation. But this solution is particularly useful because the plane wave is easy to understand and also easy to analyze. So in this expression, this k is the called wavefront vector or wave vector, and the wavefront is a plane, and this vector is perpendicular to the plane, which is the wavefront of this wave. So this is a key point of this session. Thank you.